Okay, welcome back everyone. So our final piece of today's lecture is we're just going to go through some review problems. I've selected some multiple choice problems because they're really good at sort of fleshing out some of the underlying misconceptions of the physical concepts in this sort of, well, in all the chapters, but specifically historically, I found this chapter specifically students really struggle conceptually. So I really wanted to do a conceptual review with you guys. So I put together some review questions. Here, let's just, I guess, go through them. So question one, an observer is standing at point O. So point O would be here, and is facing a mirror and observes a light source S. So I guess there's a candle or something like that. Located here at point S, where positions, 1, 2, 3, or 4, where does the observer O perceive the image of the source in the diagram? So if you see a candle here, when you're standing here, where are you going to see the candle? Just for the sake of argument, I'm going to open up the chat here. I'll see what you guys sort of type in. Type in your guesses into the chat. You can either type number 1, number 2, number 3, number 4, or the letter S. Rachel thinks 2. Anyone else? I don't actually know how many people came back after the break. Kenneth, 2 and S. Well, 2 and S isn't one of the multiple choice options. 2. Karen says 2. Okay, I think I agree. I think the answer is going to be 2, and because that's the location of the virtual image formed from the candle here. So, if we extend the mirror, then the light rays, from here are going to bounce and then bounce backwards, but then they're going to be traced back to location 2. So it will certainly be an illusion. It's not a real image, it's a virtual image, it's an illusion, but it will certainly come as if it's coming from position 2. And you can sort of, convince yourself of this by looking in a mirror that you may or may not have around your house as well. Okay, moving on to question 2. So in a double slit experiment, when the wavelength of light is increased, the interference pattern will spread out, stay the same, shrinks together, disappears, or E shifts towards the interference pattern for that of a single slit. Rodrigo says A, it'll spread out. When the wavelength of light is increased. The wavelength of light is increased. So someone says A, it'll spread out. Only one person has an opinion. Okay, well, let's take a look at this equation here. So the Young's double slit experiment, D sine theta is going to equal m lambda, and sine theta we said was going to be approximated by ym over L equals m lambda. Kelly says shrink. So we'll keep going for a second. If we're solving for ym, is going to be m lambda L over D. So here is the equation that we're looking for. So the question is, in a double slit experiment, when the wavelength of light is increased, the interference pattern will do what? And when the wavelength of light is increased, that means lambda is increased. That means it's going from, say, blue light all the way to red light. When the wavelength is increased, you see here that as lambda goes up, Ym is going to go up. So that means the distance y, the vertical distance y, is going to get bigger. So the y value is going to get bigger, which means it's going to spread out. Okay. Question 3. The diffraction pattern shown below arises from a single slit. So we're telling you that in advance. If we would like to sharpen the pattern, sharpen it meaning making it not so fuzzy, which again in turn means making the central bright spot more narrow, what should we do to the slit width? Should we cut the slit width wider? Should we narrow the slit width? Should we make the screen bigger? Should we close off the slit, or should we make the screen smaller? One person says A, narrow the slit. One person says B, widen the slit. So those are opposites. Kelly says widen, that would be B. Only three people have a guess. Well, if this was on an exam, which it easily could be on the exam, what would everyone else answer? 3 of you guys were brave. Thank you for being brave. What would everyone else answer though? Like if this was on the exam and it was a multiple choice question, presumably you wouldn't leave it blank. You would guess something. Someone says A, narrow. Okay, beautiful. So that's 4 people. Anyone else? Another A. So democratically, A is seeming to win. So let's pull out the equations here. Let me just flip back to here. Oh, come on. So the equations, if we look, if we remind ourselves, oh, there it is right there. So this is for the dark spot. And the bright spot is the same as the dark spot for the double slit. So it's similar, but a little bit different. But so here, if we wanted to sharpen it, don't forget here we would say d ym over L equals m lambda. We would swap out the sine theta with ym over L. So if we want to shrink ym, again, we can solve for ym. Is going to be m lambda L over d. If we want to shrink ym and make ym smaller, then what we have to do is we have to make the right-hand side smaller. And the way to make the right-hand side smaller is to make d bigger, because that would make the fraction smaller. So if we go back to our question here, we need to make the slit width bigger. So the answer is in fact B. So this is a good example, I guess, is why we're doing this. You know, there seems to be some misconceptions that are happening, which is, you know, exactly the reason we're doing this review. I think only one person voted B. I guess this is another good reason why science is not dictated by popular vote. Okay, number 4. Imagine holding a circular disc inside of a beam of monochromatic light. So remember what monochromatic means. Mono meaning one, chromatic meaning color. So monochromatic means one color. If diffraction occurs at the edge of the disc, the center of the shadow will be bright, dark. Okay, so darker than the rest, a bright spot, bright or dark depending on the wavelength of light that's used, or bright or dark depending on the distance to the screen. So cast your votes. You can type them into the chat. So don't forget, diffraction means like bending. It diffracts around a corner. So when light passes over the corner, it will bend. It won't just go straight. It'll bend around the corner. Any ideas? Someone says D, bright or dark depending on the distance to the screen. Kelly says B, a bright spot. 2 people, 3 people. Someone else also says B. B, lots of B's coming in. Okay, so a fair number of you said B. So let's look at it. So here, if this is the disk, and let's say this is the screen, then if light comes in and bends or diffracts, then it'll bend a little bit and hit the screen. And then this one from the bottom will bend and hit the screen. Now, this it's deceptive, but it may immediately look like it'll be a bright spot, but let's look at this a little bit more closely. Remember, the whole premise in this entire chapter is how waves can superimpose on each other. And if they superimpose out of phase, you get a dark spot. And if you superimpose in phase, you get an extra bright spot. So yes, they're meeting up here. The question is, are they meeting up in phase or are they meeting out of phase? And this question of phase is a function of path difference. So the path difference is really what's important here. So if we look at the path that these light rays take, then the light will go from here to the center, and the light ray will go from the center to here, and this is an equilateral triangle. So in this case, the path difference is equal to 0. The top light ray travels exactly the same distance as the bottom light ray, which means the difference of the paths is 0. So they're actually going to reach here, they're going to reach in phase. And if they reach in phase, they will constructively interfere. And yes, the answer is B, they will form a bright spot. Delving a little bit deeper here so we can all be on the same page. Conceivably, it's understandable the answer may have depended on the wavelength, presumably, but in this case, it's the central, like the central bright spot, the one that happens at the middle. So that the location of the center, the central bright spot is never a function of lambda, because that's always the central bright spot. That's when m is equal to 0. So m lambda, 0 times lambda is 0. And then you're looking for the angle where sine of theta is equal to 0, which is a theta of value of 0. So the path for the central bright spot, it's never a function of lambda. And D, if we look at D, distance to the screen, you can see here in the diagram, I could have drawn the screen really close, I could have drawn the screen really far. It doesn't necessarily change in any way the path difference between the top ray and the bottom ray. It changes the total length, for sure, and it might change the size of the center bright spot, that's true, but it doesn't change the path difference between the top ray and the bottom ray. Okay, good questions, good questions. I like how we're hammering out some misconceptions here. Okay, jumping back a little bit into optics or reflection and refraction. So a light ray is refracted through 3 different materials seen in the figure below. Rank the materials according to their index of refraction, least to greatest. Now remember, the index of refraction is a measure of how much bending happens. So the more bending happens when the index of refraction is larger. So take some time and see if you can rank the bending and see if you can come up with the proper ranking. And whenever you're ready, you can say A, B, C, D, or E. while you're thinking and while you're trying to work it out, I will remind you of Snell's law. We know that things will bend away from the normal when it travels into a faster medium, and it bends toward the normal when it travels into a slower medium. So you can use concepts from Snell's law to help you here as well. We have one person that voted B. Someone else said A. B. Oh, now we're getting somewhere. A, B, A. Or no, B, A, B. Sorry. B, A, B. B, A, B, B. B. Okay, so we're getting a lot of B's. We got one A. So for the sake of time, because there are other questions to do as well, let's go through it. Thank you for all who have given their answers. So like I said, the hint was Snell's law. So let's look here. If we extend this line right there, it got bent, obviously, because it's going into a different medium. The question is, did it get bent toward the toward the normal or away from the normal? So the normal of the surface is, the normal of the surface is here, and it looks like it got bent toward the normal of the surface. So this tells me that the index of refraction of 1 is smaller than the index of refraction of 2. That tells me the speed of light in material 2 is slower than the speed of light in material 1 because it got bent toward the normal. So there's at least that. 1 has to be less than 2. So that immediately crosses out C, and that immediately crosses out E as being wrong. D doesn't even make sense because there is no 1. I don't know if that was a typo. I probably typoed that, but D is probably wrong. So it's either A or B, which fits, I guess, with what everyone was responding with. And the last thing, this other one here, if we extend it, that's where we want to go. And the normal is here. So this got bent away from the normal. So this tells me that material 2 is in fact larger than material 3. So that would make this one wrong because this says material 2 is less than material 3. So this tells me that A is wrong. So the answer is in fact B. So for everyone who said B, good job. It may have been a guess for some of you, or maybe you got it, I don't know. But the beautiful part about multiple choice is, doesn't matter as long as you get the right answer. Okay, we have a few more to do. I'll pick up the pace because we only have 3 minutes. 2 rays of light from the same source destructively interfere if their path lengths differ by how much? So 2 rays of light from the same source will destructively interfere if, an overwhelming majority of people say B. Yes, the answer is B. Now, I mean, that's not the only answer, of course, but it's definitely not the other ones. It's not a quarter lambda out of phase or 3/4 lambda out of phase. Lambda out of phase would actually be bright, and these ones would all be kind of middle. These wouldn't necessarily be bright or dark, but lambda over 2 would have worked. 3 lambda over 2 would have worked. 5 lambda over 2 would have worked, but those aren't options. But out of all the options, lambda over 2 is the only option. 7, which of the following pairs of light sources can be made to be coherent? Coherent means everything is lined up and traveling together. Can two candles be made to be coherent? Only one source and its image in a plane mirror. Are they coherent? 2 pinholes uniformly illuminated by the same point source. Are those coherent? And two headlights of a car. Are those coherent? 2 images of a point source due to a reflection from the front and back surfaces of a soap film. Whew. Okay, so can be made means, is it possible to do it? Number one, 2 candles. Is it possible to have 2 candles coherent with one another? There's no physical mechanism that I can go into the candle and control, you know, if both candles emit light as a cosine wave versus a sine wave. If one starts at a maximum, the other one might start at a minimum. I have no way to control that. So candle is right out. There's no way to control that. I cannot make those to be coherent with one another. One point source and its image in a plane mirror. So if I had, you know, a candle and a mirror and then the image of a candle, could that possibly be made to be coherent? The answer is also no, because when the light wave hits a solid object, it reverts to be out of phase. So this is out of phase. And we learned this in Physics 136 when you had standing waves on a string. When we studied it right at the end of 136, when it hits a boundary, it reflects backwards, but it inverts. So it'll be out of phase. So if it strikes an object and reflects backwards, we know for sure it'll flip to be out of phase. So the answer to this one is no. 2 pinholes that are uniformly illuminated by the same point source. Well, that's true. If it's the same light source, then if you have one candle and a pinhole, 2 pinholes, then it's the same light hitting both pinholes. So the light on the other side will be in phase because it's the same source of light. So yes, 3 will work. 2 headlights in a car, same thing. When you have a light bulb, there's no way to tell that the glowing from a light bulb is the same as a candle. There's really no way. There's really no way to tell there. And 5 is 2 images. 2 images of a point source due to the reflection from the front and back surfaces of a soap film. 5, well, actually, we know 3 has to be right. So actually, the only one with 3 in it is 2 and 5. So what did I say 2 was? 2 light sources in a, 1 point source and its image in a plane mirror. Its image in a plane mirror. I'm pretty sure that's out of phase when it hits. That's the same principle as image in a plane mirror. I'm pretty sure that'll be out of phase. I'm reasonably sure that'll be out of phase. 1, here, 2, so 2, well, let's do 5. Let's see what we get 5. 2 images of a point source due to reflection from the front and back surfaces of the soap film. That definitely can be made. You can choose the thickness of the film to either do constructive or destructive interference. So 5 is definitely a thing. And 3 is definitely a thing. So 2, I guess by multiple choice, 2 must also be a thing. To the point source and its image in a plane mirror. I'm pretty sure when it strikes that surface, though, it will invert. Yeah, there's something fishy about 2. Something fishy about 2. Anyway, it looks like the multiple choice, based on multiple choice, the answer is going to be C, but I'm certain that when light hits an object and reflects, it will change its polarity. Anyway, I know we're slightly over time. We only have 2 more questions to go. Very briefly, a single color beam of laser light falls on a thin slit, a single slit, and produces a series of bright and dark spots on a screen. If this apparatus, slit and screen, is to be submerged in water, the dark spots would do what? What would the dark spots do? And well, here, if you look, the dark spots, y or d y m over L equals m lambda. So if you look at ym, it's going to be m lambda L over d. The question is, what happens when you submerge it in water? Well, in water, you will remember that the index of refraction is a function of material. So in water, the index of refraction of water is 1.33, which is bigger than 1, which means light will slow down. If light slows down, then the wavelength gets longer. V equals F lambda. The frequency is constant. So if the speed goes down, the lambda also has to go down with it. So, or not get longer, get shorter. So if lambda goes down, then this lambda goes down, which means this lambda goes down, which means the whole pattern will compress, it will come together. So it will not change, that's false. Will move away, nope. It will move toward, disappear, nope. Locations will not be predictable without knowing the wavelength, no. So the answer there is C. And last but not least, the formula y equals r m lambda over d for the location of the points of constructive interference from the two slits is valid when I mentioned in class that this was only for when the L value was very much bigger compared to the vertical distance here. So more specifically, or I drew that wrong. So the reason why the adjacent side needs to be really long and the opposite side needs to be really short is because we were actually getting theta to be very small. So the answer here is only for small angles of theta. So not for all angles of theta, not for large angles of theta, that's very wrong. It has nothing to do with lambda, and it has nothing to do with m values. It has everything to do with the small angle approximation, which we also talked about in Physics 136. Okay, we went a little bit over time, my apologies guys, but hopefully that review was helpful. Some of the main concepts from the previous chapter. So I'm gonna end the recording now, and I will hang back and answer some of your questions that you may have. And I will see you tomorrow in the last lecture. So please come prepared with any course-related questions you may have. They could be from Gauss's law back at the beginning, or they could be from today's lecture. It doesn't really matter. Okay, guys, I will see you tomorrow.